to Study Time, a televised home learning program produced by Rwanda Education Board.
Welcome back. This is Mr. Simon, and we are here to change our world with chemistry. So we are still on our topic of conductivity of solutions and unit number 12. And today we are going to be talking about molar conductivity. Molar conductivity. When you hear the word molar, you recognize that now we are dealing with chemistry. Unlike last time, we are dealing with chemistry. But last time we had stayed with some questions, and I want to show you some of the answers we managed to get. For example, number one, those are our answers. You can check your work and see if you have those answers in the, And number three, those are answers. You can check your work. You can check your work. So we're going to continue very quickly about molar conductivity. When you hear the word molar, you know now we are going to relate conductance of electricity with the molarity. So what is molar conductivity? Molar conductivity is the conductance of a solution containing 1 mole of an electrolyte placed between electrodes 1 centimeter apart and having a cross-sectional area of 1 centimeter squared. Or we can use meters. We can use what? Meters. So from our definition of molar conductivity, we can say that molar conductivity is going to be our symbol. Is going to be our symbol for molar conductivity is equal to the conductivity, electrolytic conductivity, or what we call specific conductance, divided by C, which is going to be our concentration. So we can remind ourselves about this. We can call it electrolytic conductivity, and C, which we're going to call our, normally we call it molarity, or we can call it concentration in moles per decimeter, or moles per what? Per liter. So, but remember, if you remember very well, you said K is equal to conductance times L, which is the distance between the plates, divided by, thank you very much for remembering, cross-sectional area. And we said the units of K are per ohm per centimeter, or we can say per ohm per meter, or we can say Siemens per what? Per meter. So, but now let's derive the units of molar conductivity. This big man here, molar conductivity. So as you've seen from my expression here, we are saying that molar conductivity is equal to K, which is let's use centimeters. So supposing we have per ohm per centimeter divided by, normally this is moles per decimeter cubed, but let's just say we have already changed the units and we say moles per centimeter cubed. So meaning the units of this guy, which is molar conductivity, will be, so we cancel, so this one will go up. Let's do some simple mathematics. Per mole, per ohm. Then when this one goes up, it subtracts with this one. When it goes up, it will be this one times this one cubed, then per what? Per mole. So we say -1 plus 3. And we shall have per ohm, centimeter squared per what? Per mole. We can say per ohm, let's say meter. Meter squared per what? Per mole. We can say Siemens, centimeter squared per what? Per mole. These are all units. Even we can say Siemens meter squared per what? Per mole. Like that, even others. So we are using two units. We are using meter squared and centimeter what? Squared. So, but those are units for distance. Yeah. So if you look at our screen very well, we have the units there. So, but it is good to note that because this, in our calculations, if you have molar conductivity is equal to K. This K is normally per centimeter. And this C is normally decimeter cubed. So, to cater for unit change, we multiply times 1,000. Times what? 1,000. So, meaning that you calculate, as you're calculating, you don't need to change the units if you multiply by 1,000. That is, if we have, for example, C in moles per what? Per decimeter. And the K in per ohm, centimeter squared per what? Per mole. Okay, it's mistake. So let's not say, it's not like this. We're going to say K in per ohm per what? Per centimeter. Per ohm per what? Per centimeter. So to cater for unit change, you multiply times 1,000. Then if we have our units in meter, that is, if we have K over C, we shall divide by 1,000 in our calculations. So we have C, again in moles per what? Per decimeter. Then we also have this K in per ohm per meter. So when you divide by 1,000, you cater for the change in units. Or you can change them as you calculate. If you remember very well, also when we are dealing with the moral concept, something similar, where we say that our number of moles, we can say our molarity is equal to number of moles over volume times what? 1,000. So when you multiply by 1,000 like that, it means this volume, which is in centimeters cubed, has been changed. Has been what? Changed. So you don't need to change the units. All you need is to calculate. So our next part is calculation. So if we want to calculate molar conductivity, and these units are in moles per decimeter cubed, and K is in per ohm per centimeter, meaning we use this one. We use this one. Then, if it is in meter, we use what? That one. So it means this one will give rise to units like this one and that one. Then this one will give rise to units like this one and what? That one. So, let's continue and look at our calculations using this expression of molar conductivity. So we have some examples here. We are going to calculate some of them as we practice. So the first question is saying a solution of 0.2 molar potassium chloride has an electrolytic conductivity of 2.4 times 10 to the power negative 2 Siemens per centimeter. Calculate the molar what? conductivity. So this question is a quick application of one of the formulas we have here. Like for example, number 1, we can say solution to our problem. So the first thing we are going to note is good for us to first identify the units. So the units are in per centimeter, the units of electrolytic what? Conductivity. So we are going to say, we are going to use this one. We are going to say that this C is equal to conductivity over C times what? 1,000. Then after we substitute. So we substitute where we have 2.48 times 10 to the power negative 2 divided by our molarity. We divide by our molarity. So we can do like this just to save our blackboard. We can do like this. Oh, let's leave it. It's wastage of time. So you just calculate. So as we have said, we multiply times 1,000 to cater for unit what? Change. To cater for unity change. So we are going to do like this. So we say, you calculate very quickly and see if we can get the same answer. Make sure you always come with a calculator, because in this topic we do a lot of calculations. So our answer will be 124. So because our K is in per centimeter, so we are going to say again our will be per ohm centimeter squared per what? Per mole, according to our explanation here. So because you multiply by 1,000, we don't need to change the units. It always gives you the units automatically. So let's look at number 2 also. Let's quickly look at number 2. Number 2 says a solution containing 0.208 gram per liter of barium what? Chloride has electrolytic conductivity of 268 times 10 to the power negative 4 per ohm per centimeter. Then calculate the molar conductivity. The molar what? Conductivity. Again, we are going to employ our rule, but this time they have not given us C. They have given us concentration in it. If you remember our topic, we said concentration in gram per liter. We can as well know that our mass is equal to number of moles times molar mass. So this is our mass in 1 liter. The number of moles in 1 liter, also which is molarity times molar mass. So but we need molarity. So molarity will equal to concentration in grams per liter. Students are following. Divide by molar mass. Divide by molar mass. So you see, this time we need to get the molar mass of barium chloride. So let's get the molar mass of barium what? Chloride. So barium is, if you look at our question, we have these values. That's 35.5 times 2. Who can get for us the answer? So what will be the molar mass? We can use a calculator, or we can use our head. So we say 137 plus 35.5 times 2. So our answer will be 208 gram per mole. Gram per what? Per mole. Yeah. So we are going to say our molarity. This time we are going to, now let's change it to C, because it is in our formula. Will equal to 0.208 gram per liter divided by 208. So that will be our C. We are going to say 0. These mathematicians now know the answer already. Yeah. So we have 1 times 10 to the power negative 3. Oh. Are we together? Are we together? So, from there, we go and get our expression for molar conductivity, which is equal to, so we have our units, this time units of conductivity are in centimeters. So we are going to say K over C times what? 1,000. So we are going to say we have our K value is 2.68 times 10 to the power -4 divided by 1 times 10 to the power -3 times what? 1,000. 1,000. So we shall say is 2.68 times 10 to the power. You calculate and see if you can get the same answer. Divide by answer times 1,000. So our molar conductivity will be 268 per ohm. Centimeter squared per what? Per mole. Centimeter squared per what? Per mole. So hope we are together and you are following. Yeah. So we are going to do also number 3 very quickly. Let's do number 3 very, very what? Quickly. We can give you some little time to look at our answer and you copy the answers. Only a few minutes before we go to number 3. Actually, a few seconds. So number 3 says that a solution of an electrolyte of 0.02 moles per decimeter cubed has resistance. This time they have given us resistance. And a cell constant. Do you remember cell constant? Yes. Calculate the molar conductivity of the electrolyte. Yeah. So again, our molar conductivity is given by the same expression. So this time what we don't have is K. Is what? K. But remember we said that this K is the conductance of a solution placed between electrodes 1 centimeter apart or 1 meter apart and of cross-section what? Area. So but we said this G, but G, which is conductance, is equal to 1 over R. So our conductivity will equal to 1 over R, well, let's say L over R A. So we are going to look for K. We are going to look for K. So, but remember they have given us the cell constant. So our K will equal to 1 over R times L over A, which will equal to, now let's substitute. Hope you are following. So here we have 1 over 0.357 times, yeah, our cell constant, which is 1.5. 1.5. So we somehow moving slowly such that you can follow and be able to even to note down our answers. 0.357, yeah, times 1.5. So our K will equal to 4.20168. Actually, it is good to remember that when you're calculating, it's good to write very many decimal places like 4 to make sure you get an accurate answer, because this is a part of the answer, but it's not the final answer. So meaning it is a continuation. It is a what? A continuation. So this is our answer. Then we are going to come here and say, but the teacher has, today we have studied and said that molar conductivity is equal to the conductance, conductivity, let's say conductivity, divided by concentration C. Now we have this and what? This one. But this one is in meter. So we multiply here by 1,000. By what? 1,000. So our K, which we have got, which is actually 4.20168 divided by 0. 0 point what, class? 0.2. 0.02 times what? 1,000 times 1,000. So you calculate, make sure you calculate through. So we have here divided by 0.02. Who has got the answer? Divide by what? 1,000. So answer will be 0.21. Yeah, this is the final answer, even if you write few decimal places. And say per ohm meter squared per what? Per mole. Yeah, we'll give you some time to copy the answers. To copy the what? The answers. So you see. So in these calculations, it's always good to remember our formulas. Always remember the formulas. And also substitution is very, very important. Correct substitution. Correct what? Substitution. So as we continue with our calculations, let's first leave them for some time. Then we have a little bit of discussion. There are some important terms in molar conductivity. These two terms we are going to talk about. One of them is ionic mobility and ionic what? Interference. So when a solution is conducting, for example, when current passes through a solution, we say it is conducting. It is what? Conducting, because there is movement of ions. If you have electrodes, the ions sometimes move towards the what? The electrodes, as you know in electrolysis. So there are factors which will determine our conductivity. But before we talk about those factors, there are some things we need to talk about, things like ionic mobility. We should know that these ions in solution actually move. They actually what? Move. So we are going to say that ionic mobility, we can say the average velocity possessed by ions and a PD of 1 volt, potential difference. Or we can easily say ionic mobility, the movement of ions. The movement of what? Ions. Their ability to move in solution. And we are going to say that the faster these ions are, the greater the molar conductivity. Like, for example, we have said, if you look at your screen, that the higher the ionic mobility, the greater the conductivity. So the faster they are, the faster the what? The conductivity. Or the greater the what? The conductivity. So this conductivity depends on two factors. Very many actually. Here we have 3, but we can have even more, as we shall see in our next lesson. Like concentration of an electrolyte. Meaning if the concentration of the electrolyte is high, the ions will not move freely. Will not move what? Freely. You just imagine you are moving and you observe that, this time, you observe that there are very many people, or like, for example, you are driving a car, and there are very many cars in the way. Normally, we call it traffic jam. There's a lot of traffic. Like, for example, in Remela, a lot of traffic. So when there are very many cars, the movement of the speed of the car will be very, very slow. Very, very slow. But if the cars are very few, and the driver wants to move very fast, it is very easy for them to move very fast. So even these ions, we have the same situation. If the ions are too close to themselves, it becomes very difficult for them to move. Very, very what? Difficult. And then that's why we shall say that if concentration is high, mobility will be low and the conductivity will be low. If concentration decreases, meaning if we have more of water or solution, the ions are free to move. So when they are free to move, meaning they will have a higher mobility in case we have connected electricity. A higher what? Mobility. And the higher the mobility, the greater the conductivity. Let's also talk about temperature. Let's talk about what? Temperature. Temperature also can affect the speed of the what? The ions. If the temperature is high, the ions are activated. They can easily what? Move. So if they can easily move, then we shall have higher what? Conductivity. If the temperature is low, the ions are not motivated to move. And when they are not motivated to move, you observe that our conductivity will be very, very low. Another factor which can affect our ionic mobility is charge. Is what? Charge. If charge is very high, you know charge. If charge is very high, like for example, when you have aluminium 3 plus, aluminium 3 is having a high charge. It's having a very high charge. And then we have magnesium 2 what? 2 plus. And then we have sodium 2 what? 2 plus. So we are saying that if we have an electrode and all these ions are supposed to move towards this electrode, so the one which will move faster is the one which will have a higher charge. So aluminum will move what? Faster. But also depending on if keeping other factors what? Constant. Keeping other factors what? Constant. So another factor we shall talk about is the ionic interference. You know the effect of an ion caused by other ions as they move in solution. As I was giving you an example of cars moving in traffic. When the cars are very many, it is hard for them to move, and sometimes there are even small accidents. So why? Because they are interfering themselves, interfering them. Even these ions, when the ions are very many, the interference becomes very, very high, very, very what? High. If the ions are very few, the interference becomes very low. And when the interference becomes very low, the ions can easily move, and then we can have high what? Conductivity. So we shall talk about those things next time. I've given you a question here to do. Make sure you note down that question. Use what we have discussed in the first lesson and this lesson we have talked about today. Make sure you try out that question. Make sure you try out that what? Question. So the question says that a cell with electrodes of 0.002 meters squared of area and 0.1 meter apart is filled with 0.1 molar aqueous solution of sodium what? Chloride. So the molar conductance is that one. If the EMF is that one, calculate the current. So you can use many equations we have discussed to do that question. Thank you very much for following me today. Hope you've got something and you've added something on your life. Hope we meet next time. God bless you very much.